okay, how do we now find an AC model for this and start to close the loop? Because I want to do an example all the way through where we have a buck converter into its continuous conduction mode, which means, again, the inductor current doesn't dry out at the end of the D prime cycle. And then put all together the circuits to see how do you get the loop gain and how do you get the transfer function from input to output, an AC transfer function over the whole loop gain. How do you determine the loop stability, the phase and gain, and how do you get an injection like a load current into the output, sinusoidal? What does the output impedance do over the loop gain? And so we want to begin with how do we get an AC model? And so that's what we're going to do. And without going to state space averaging equations and deriving it that way, even though that's how I derive it in the advanced books that I have. So this gives you an idea. I found a real good trick. It gives you an identical answer, and it's just intuitively and easy to follow. So let's begin doing that, how to develop this AC model for what's called the power stage on the buck. So we have a signal, sinusoidal V sub G on the input, and we're going to have a DC input, which is VG. The hat again signifies that it's AC. And then IG is in a general state. If I don't do a hat or anything and call it small I, then that stands for AC. It could be AC and DC. So what do we have here on the duty cycle? Well, you see the duty cycle is going to have a DC duty cycle turn and then what's called a D hat turn. And how I'm going to explain that is what's happening is here's your duty cycle coming in, and that's the duty cycle DT. And the hat would sort of be on the next cycle because you can't get on the same. So this is the T. And on this next cycle, there'll be a small perturbation here. And that small perturbation in duty cycle is the D hat T. And that would be, of course, your regular DT here. So we could see that what you want for small signal analysis is that D hat over D must be much less than 1. And this is the AC signal. It's small signal analysis. You do that with everything. You do that with amplifiers. When you bias a Class A amplifier and you bias it with your DC and get your midpoint, and then you put a small signal AC on it with a gain on the output. So you're doing the same thing here. You're just doing a small signal perturbation to get your small signal so that you can determine your loop gain, because the loop gain is the small signal analysis. Any large signal analysis like pulse transients, loop gain is gone. You don't even consider loop gain because any large signal is going to saturate the op amp, and in a saturated loop, there's no loop. So this is all small signal. So then we have your diode here, freewheeling diode. You have your inductor. And again, this current here is going to be a DC term I plus an I hat, an AC term here. And then your output voltage is going to be a DC plus a hat turn here. So if we look at this here and we want to derive something very quick for the small signal, we notice that this point right here, what would it see? Well, it sees really the product of this times the duty cycle, this. And you can see that from here. That's what generates this square wave right in here. That's what generates the square wave across here. So in reality, what you have across that for a square wave is you're going to have the VG plus the VG hat multiplied by the duty cycle, D plus D hat. And it's that simple. And you could see you're going to have the DC term. You're going to have an inner term that's one AC term, a DC times an AC, plus the second one is going to be VG times duty cycle, and the last term is going to be VG hat D hat. And this is the DC term, and since this is an AC analysis, we don't want the DC term. This is a nonlinear term. Nonlinear term. So what we're going to do is we're going to say, of course we're going to say the VG hat over VG, we want to be much less than 1. Also, we know that for small signal, D over D is much less than 1. So then the product of this, you see, is going to be much less than 1, and we're going to ignore it. Okay? And of course, since the DC term is here, we don't need to put the DC term in because we want an AC model. So hence, what we have there is we have the AC model for this output section here. And then we're going to find, well, what's the AC model for this input section here? Well, what we have here is, you see, this is I plus I hat. When the switch is on, it's going to see I plus I hat. And when the switch is off, it's going to be see no current flowing here. So this current that flows into this input section is going to be related, just like we did before. It's going to be related to I plus I hat times the duty cycle, this duty cycle here, which is going to be D plus I hat. So again, we're going to have a DC term, we're going to have an AC term, a DC times an AC, and we're going to have another AC term. I'm sorry, this is I plus I hat, this is D hat. And we're going to have I D hat. And then the last term is the nonlinear. Again, we're going to ignore it for the same reason. We don't need the DC term. And so this is the two AC terms. So we have two AC terms here, two AC terms here. So what we're going to do now is to say, fine, can we put a model here? Well, sure. Let's do these terms here. What do we have? We have two terms. Remember, we have a D, VG hat, and we have a VG, D hat. It adds. So how does voltage source add? So we have this term here, which is going to be VG, D hat. And we have this term here, which is going to be equal to your D, VG hat. Okay, that goes where? To the low pass filter, where that current is I. Now, remember, AC only, it's just I hat. And the output, AC only, is V hat. So that's our output section here. Okay. Now how about this input section? What about these current sources? Well, we have a DI hat and we have an ID hat. Well, that's right on the input source. And again, we're only interested in the AC VG hat. The DC goes to 0. So when you do an AC analysis, you short out your DC sources. That's why the DC doesn't approach. So now what do we have? We have two current sources. And the current sources go into the circuit, into the switch this way, so that's why it's down. And that is I, D hat. And then you have the other current source. How does current source adds? They add in parallel. That's how you have the sum. This is the D. This is the D ID hat, plus D I hat, correct. So this is your sum of ID hat plus D I hat, and this is then D I hat. So this is our AC model. You could see there's kind of like a transformer action that Dr. Middlebrook put together, and he says, look, this is kind of like a transformer action. And this transformer action means that, look, I have VG here, hat, and over this side I have D times V sub G. Okay, I have I hat here, this is I hat, and on this side I have DI hat. So you could kind of look at this as saying, well, you know, it looks to me like I have a little transform. You consider it as, of course, ideal, which passes DC and AC, which, of course, that transformer doesn't exist. But that's what they likes to put it, and he uses a symbol, Dr. Middlebrook, like this, to say it transfers DC and the AC. And the turns here is D, 1 to D. And you still V sub G, plus minus, that's this person here, which is your VG DC term times an AC term, and then you have your low pass filter. Okay, that's your low pass filter. And you have your V hat. So you see, let's see what we have. See, VG is here, so what do you think is across here? Well, that's just DVG hat. Well, that's the same as this. That's where you got it from. Okay, that fits. How about this current that flows in here? Well, that current, if this is here is I hat, then it goes by D, the opposite turns ratio is DI. So this is DI hat. Oh, well, that's the same as that current. So you could see that that clearly is the model. The strange thing on this too is you could turn all these into DCs. Remember, it can transfer DC, and this would be DVG DC term. And if we consider DC term, then this here would be considered a short, and you'll basically have your DC analysis too. If we turn this into a DC and this is DVG, then what happens is the voltage here is a V hat. We set that to 0 because we're interested in DC. And we put back this, and the only current is DC. And then this is DC. And we make that as a DC. So what is this inductor for DC? Well, that's a short. The capacitor is an open. So you could see that the output immediately is DVG. And we have our DC characteristic too. V over VCG is equal to duty cycle. V over VG is the duty cycle. And that's just your check. The same thing is as with the current here. The DC current is going to flow through the load. Remember, all the ripple current is going to only flow through here. So therefore, I is equal to V over R. Now, if we wanted the current on the input on that, then you're going to see that the input current, if we branch this as DC, then it's going to, this AC is going to go to 0, but I'm going to still have, again, the transformer reflecting back the current, reflecting back this current, the same as this current, I, to the other side, and it's just going to be the current D times I. Meaning that the average current of the generator that the generator sees is going to be D times I, but I is V over R. So you could see then that again, I is V over R, or that the input current is the average of the output current. Okay? So that's kind of a check that says, oh, well, it kind of works for DC as well as for AC. But again, what we're interested is only the AC model. And so when we put the AC model together, we just have what we have here, which is the AC model, VG hat. I'll redraw it. So we have this current here. That's I d hat. And what we have here, you can lay this out to 1 to D. We have V DC term times a hat. You always know when you have a product, one has to be DC, the other has to be AC. And the reason why, or it'll be nonlinear if they're both AC terms. It's a product of an AC term, which is nonlinear. Okay, so this is what we have. Now, from this, we want several conditions. Number one, we want to be able to determine, first of all, the transfer function from output to input. We also want to know the transfer function from output to duty cycle. Okay? And we have 2 duty cycles here, one hat and one here. Okay, so in order to do that, this is an AC model. There's nothing DC, it's a linear AC model. So we can use what's called superposition. And let me add one more thing. We're also going to add an output pulse, and that's going to be, I don't want to get to the I hat, but that's an I-O hat, the output current being injected in, not the I hat, not the I hat that goes from the inductor here. If we inject this into here, that also is going to move the output voltage, the AC. So it's a small signal injection of current to the output to see the response. So what we're going to do now is to have, okay, if we want the output voltage over the input voltage, let me write that better. We want the output voltage over the input voltage. Then we're going to set D hat equal to 0. Also, we're going to have I-O hat equal to 0 because we don't need those. Because it's a linear circuit, superposition says the output voltage is the sum of any combination of sources, linear, since it's a linear circuit. So if we set these two to be 0, how do we set a current to be 0? We set a current to be 0 by opening them up. You set a voltage to be 0 by shorting it. So this is a current source. So therefore we open it. So we have here now VG. And we have an open for this. Okay. Then we come back. We still have a transformer. 1 to D. And what do we have here? This circuit here is a short. That is VGD hat. Because we're setting this to 0. Just like we set ID hat and we set this one to be 0. That's an open. The current source, voltage is a short. We put back the inductor. We see that's I hat. And we put that to voltage. V hat. Okay? So now we have our circuit and we need output to input. Well, that's pretty easy because now what is the voltage that I see across here? Well, that's just the turns ratio D times V sub G hat. So you could see, you could redraw it nicely if you like. You have this AC, that's DVG hat. And you come into this low pass filter. And now that's easy to do is because we have just a resistor divider, impedance divider. If we call this ZO and this is ZS, you could see that the output to the input voltage, DVG hat, is going to equal to ZO over ZO plus ZS. So instead of writing this down all the time, we just represent that as what's called H of S. And H of S is this low-pass filter, known as the H of S is the low-pass filter block. Because I don't want to keep writing out ZO over ZO plus ZS. So, but wait a minute, this is I don't want the D on the bottom, so I multiply both sides by D. Multiply this side by D, of course it'll be this by D and this by D. And we got our transfer function that is equal to V over Vg, which is equal to D times H of S. And that's one of our AC states to say, now what does this say? First of all, it says that the AC source gets attenuated by D. Well, that makes sense because the AC on this side gets attenuated right here by D. That makes sense. Then it gets attenuated also by the low-pass filter. So as long as the low-pass filter is lower than the input circuit, remember, VG is not the switching frequency. It's any added signal that you go. And that could be from other inputs that get the AC waveform, which is 120 hertz after a full bridge. It gets all kinds of signals onto the input from other converters turning on and off in the input stage. So that represents low and high frequency. It has nothing to do with switching frequency. Okay? So we have our transfer function. And like I said, you could see that the output voltage, one of them is now D H of S times VG hat. So you could see if you put in, for an example, let's have a D equal to 0.5 duty cycle. Okay? And then H of S, the low-pass filter, let's say we have a breakpoint at 1 kilohertz. Okay, and let's say we want to put a noise signal at, say, 10 kilohertz. Okay, at 10 kilohertz, we're going to put in the signal. So we're going to put in, this is going to be DH of S, and we're going to put a signal of VG being equal to Vm sine omega t. And the omega, we're going to put a 1 volt signal in, 1 volt, at a frequency of the 10 kilohertz. So sine 2 pi 10k t. Okay? 2 pi f. Now, when we do this, I want to know what we get out. What does the output look like? Well, if that's 1 volt, you know it's a sine wave. It's going to get a sine wave out, but it's multiplied by this. So the output is going to be a 0.5. Well, what is this? Well, this is going to be the low-pass filter. So since the breakpoint is 1 kilohertz, by the time it hits 10 kilohertz, that's minus 40 dB down because the slope is 40 dB per decade. Well, that 40 dB is a factor of 100 because 20 log of 100 is 40 dB. So you see, this gets divided by now 100 times 1 volt at 10 kilohertz. So you can see that the output voltage now is going to be 0.5 divided by 100 times a volt at 10 kilohertz. Okay, so we see that this comes out to 5 millivolts at 10 kilohertz. But now another question is, what if VG now is 1 volt at, say, 100 hertz or 120 hertz, either way, say 120 hertz. That's from maybe we converted from AC to DC in a full bridge, 120 hertz. Well, now you can see at 120 hertz, the filter doesn't do anything because this starts off at 1, which is 0 dB. So this starts off at 1 for the filter. The only thing, remember, that's why I characterized the filter first. Remember, this was just the R over R plus RW, which was approximately 1. That was that K term. Okay? Which means that's 1. So in other words, the low-pass filter does not filter out 120 hertz. It doesn't even filter out all the way up to 1 kilohertz. There's no filter. So the only thing that bucks me at this frequency is going to be the duty cycle. So what we have is VH is the D H of S, and that's the VG. This VG now at 120 hertz, well, you know, this is 1 and this is 0.5. So you can see the output voltage is going to be 0.5 times 1 times 1 volt at 120 hertz, which means that the output voltage is going to be a half a volt at 120 hertz. Not very good if we don't want a half a volt right on our 5 volts or 3.3 volts if that's our output voltage. So that's not very good. So what will start to take care of this? That's where your loop gain comes in. When we cover the loop gain next, we'll see that the loop gain is going to be coming into play, and what will happen is that the output voltage, dH of S, this is the open loop gain. Okay, so the closed loop gain, which we will not derive here, I derive in other courses in my advanced course and the other courses, is going to be dH of S divided by 1 plus T, Vg. This is the closed loop gain. So when we close the loop, this will be the transfer function for input to output. And as you can see, what winds up happening is for lower frequency, then the loop gain, the gain T will be very high. And we will see when we do feedback, you always have to know what you want in your feedback loop. And what you want is an integrator, ultimately. So when we look at the loop, it's going to look sort of like this. And this is your 0 dB. And this is really the gain of the op amp that limits me, or else if there were infinite gain, it would continue going up. So usually the band with the op amp is usually about 10 hertz, somewhere around there. So you can see at 0 dB, this will be ultimately the loop gain T. This will be 20 log of 1 over 1 plus T. Actually 20 log of T, sorry. So this is what we want our loop gain to be T. Be 20 log of T. And it's going to go down at minus 20 dB per decade. And what you'll have is this here is your unity gain frequency, and you'll have your switching frequency way up here. That'll be your switching frequency. So your loop is typically closed by typically 1/20th to 1/10th of the switching frequency. So if your switching frequency is 100 kilohertz, this FU should be between 50, let's see, 1/20th, which would be, it'll be 5 kilohertz to 10 kilohertz. And that's where we're going to start, basically, is to have the loop gain, unity gain frequency at 0 dB. So that's ultimately what we're trying to achieve. That's ultimately what we're trying to achieve. And I'm sorry, this was, of course, the switching frequency would be 100 kilohertz. Okay? And so now, the other expression we need, the other expression is going to be the output to the duty cycle. And that, we have to come back to our drawing here and find out what the transfer function is output to duty cycle. So the output to the duty cycle, we're going to set VG hat now equal to 0, and we're going to set the IO hat equal to 0. And that's the output, the duty cycle in our expression. So what we're going to do is we're going to take our input to the V sub G and short it. That's VG hat. You can see that there's that current sense. We're going back to that schematic. And there's the 1 to D. And we're going to place this duty cycle back, which is VGD hat. We have our low pass filter. And there's our low pass filter. So this is R and L and C. Okay? So as you can see, if we short this input filter, this current source goes to a short and doesn't put any voltage here. So you might ask the question, why is this even present? That's where the input filter interaction would come in. If there were an input filter here, you could see then we have a superposition. We have to find out what V out to ID hat is, because now it won't be 0 voltage here, it'll be the voltage across the input filter. And then we'll have to find what V out is to the VGD hat. And that's the input filter interaction. And if you look at this, this produces a positive result here. This one, since the current's going down, if it's into input filter impedance, it's going to be the negative. So it's a reversal. So if this is going to be stronger than this, you're going to have a phase reversal in that frequency, and what's going to happen is you're going to have a 180 degrees phase shift, and it's going to oscillate. That's why with certain input filters, you can have an oscillation. That is covered again in my advanced books. We're not there. We're going to cover just this with no input filter, so therefore this is not here, it's a short. So if this is a short here, it's of course short here, it's also just shorts this right to here. That becomes a short. So basically what we have is just this circuit now, moving this down to here to make it just easier. VGD hat and our low pass filter, just like before. And remember, we characterize the low pass filter as just some H of S, so we don't have to draw Z out over divided by Z out plus ZS. We call that H of S. And to get your output to duty cycle here, VGD hat, that's just H of S again. But here we can multiply both sides by VG, and we could see the output to duty cycle is going to be VG times H of S. This will be important to close the loop, and that would be important there. So again, we're going to go through this circuits and do an example, and that's the best way we're going to try to obtain what we need to obtain. So the next section here is going to say, okay, we got one more thing to go to. We have this I/O. So we want to find the output due to this small signal injection current, and that we find by setting VG hat equal to 0 and setting duty cycle equal to 0. And what we do is we go back to the circuit again. There's your VG hat, and that's shorted. You short that. Again, it's going to short this current source, ID hat. Now, what's ID hat? This is going to be an open. That's going to be an open. Why? Because we're making D hat equal to 0, which a current source is open. A voltage source short, current source open. Then we come back and have the transformer, 1 to D. And then we come back again. This is a short because it's VG D hat, and D hat is 0. And we have this low pass filter. And remember, this is not the low pass filter you generally do. Remember, if you have DQing, you're going to put all that stage down, just as we did before. And then we're going to put this little injection back, which is the IO hat, that produces the V. So as we see, if this is shorted, it basically shorts this, and this is a short. So you wind up with what? An LRC circuit. You wind up with an L, C, and R. And looking back into here, we have an impedance. This is going to be your current source IO hat. Okay, so looking back is what we're going to look at is an open loop impedance, ZOL. And the ZOL is just like before we had the ZOL, and now we can add your parasitic in, like before. We can put the RW, which will be added an RW here, and then we can add the ESR. ESR, and we can now characterize looking at this filter, remember, by the simple thing of drawing it up. For the DC, this is a short, this is an open. We start at low frequency up to high, and we could see this is just R parallel RW. This moves up. This is going to be when this X sub L is equal to the RW. So this is going to be 2 pi F. We know it's going up. It's a 0. L would be RW. So the frequency here would be RW over 2 pi L. Then depending upon if the ESR is here at high frequency, remember this is the capacitor will be a short, the inductor would be an open, and we have R parallel with RESR. And then anywhere between this, we have the characteristic impedance, what you did before, square root of L over C. And if the resistance, load resistance, is above this, then we're going to have a Q. If it's below it, then we're going to have real poles. Okay? Just like before. That's why I did the sims. So this is really a map of ZOL. That's the open loop that we have here. So just writing this down here, we can now write the transfer function, but let's simplify this a little. For any kind of converter, RW is always going to be less than R. So that's going to be approximately equal to RW. And again, the ESR is in a matter of milliohms. That's going to be less than resistance, which is typically in ohms. So this is going to be RESR. So writing that down, we could see that ZOL is, for the DC term, would be the RW, and then we'd have this this 0 here, which is the SC ESR plus 1, and then we're going to have this S over omega 0 squared plus 1 over Q S over omega 0 plus 1. The standard transfer function that we would have on the queuing, just like we do with any queue. The last thing I want to say here is, what is the ZO closed loop? Okay? You're going to find again in the advanced courses, what we do is actually going to wind up being derived as Z open loop divided by 1 plus the loop gain T. And that's going to be the closed loop gain. Again, we're not deriving any of these closed loops. However, when we do the example, we are going to actually show that this is actually the case by deriving it by a hand analysis, an example, and then running the sim to show that they match. And like I said, in the advanced class, I'm going to prove all these impedances that the open loop is, the closed loop is equal to the open loop divided by 1 plus T. So you could see then what are we going to have for the output voltage now over, and that's going to be equal to ZOL divided by 1 plus T on closed loop. And for open loop, IO, and we'll make this closed loop, it will be just ZOL, and that's it. So you could see now by putting everything together. So for our open loop, our output voltage is going to be D, H of S, VG hat, plus Z out, ZOL, open loop, IO. And our closed loop is going to be D, H of S divided by 1 plus T, VG hat, plus ZOL divided by 1 plus T, IO hat. And so these are our expressions. And again, the best way to see that the hand analysis is going to match the simulation analysis is to actually do a specific example with real numbers so that we can do a Bode plot of the open loop and closed loop, and then do the LT Spice simulation with the same circuit and do an open and closed loop. And we're also going to get into the error amp design, which again we went through some of the pole zeros, but we're actually going to use it now. And also we need an expression from transferring the duty cycle to the error amp output.